All right, so here's what we have. 24 sorted data values that are given. We're going to find the percentile to the corresponding to the value 46. Okay? The way we find the percentile for 46, we take the number of data values that are less than 46 divided by the total number of values, and that will be multiplied by 100. So in this case here, looking at this, how many data values are less than 46?
8.
There are 8. Okay? So that means this is going to be 8 over the total number of values that's given as 24 times 100. So we have to do 8 divided by 24 times 100. Okay.
And then 33.3.
Let's see, 8 divided by 100. 24. Then times 100. That'd be 33.3, but we just round to the nearest whole number. 30. It'd be 33. And this represents the 33rd percentile. So the number 46 represents the 33rd percentile. Okay. Questions on problem number 1? Part A. Sorry. Now part B is what number is in the 60th percentile. So we're looking for the data value that's in the 60th percentile. So here we use this locator formula, which is L is equal to K divided by 100 times N. N, the K is that percentile that we have for that subscript for P. Your N is the number of data values. Since we're looking for the number that's in the 60th percentile, your K is 60. So it's 60 over 100 times N, which is 24. And if you get a decimal value, we round up to the next larger whole number. So if I do 60 divided by 100 times 24, I would get 14.4. But we need to round up to,
14.
after 14, what's the next larger whole number?
15.
15.
I thought I rounded down.
No, round up. We always round up in this case. So, to find the number that's in the 60th percentile, we look for the 15th number in this sorted data set. So in this case here, we're going to go to the 15th number. That's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that 54 right there represents the 15th number. And that's going to be the number that's in the 60th percentile. Okay. Okay. Are there any questions about part B? Now part C is the first quartile, which is in this case Q1. Okay. Now another way of writing the first quartile, or Q1, is this. Because if you recall, the first quartile represents the 25th percentile. Q2 represents the median, Q3 is the 75th percentile. Okay. All right, so now let's look at this here. L is equal to K over 100 times N. So if I do 25 over 100, times n, which is 24, was 25 divided by 100 times 24?
6.
6. So the locator, now, if this is an even number, that means we look at the position of this number and the next number after it. So that means we have to look at the 6th and the 7th number in that sorted data set and take the average of the two. That means we divide by 2. What number is in the 6th position?
38.
And what's the next number after that?
39.
39. So we add 38 and 39 together and divide by 2.
38.5.
Okay. So it ends up being 38.5. That 38.5 represents the first quartile, or Q1. Okay.
So why would we do the 6 divided, or 6 plus 7?
Because when we found out what L is, it came out to be an even number.
Okay.
Okay. If it comes out to be a decimal, then you round up to the,
But if
yeah.
it's ever even, you take the number and the one after it.
Mm-hmm.
Okay, thank you.
All right. Any other questions? Okay, now part D. Was P80, P sub 80. That's the 80th percentile that we're looking for in this case. And to do that, we always use L is equal to K over 100 times N. Their K is going to be that 80, so it'll be 80 divided by 100 times N, which is 24. Now, what's 80 divided by 100 times 24? 19.2. Now here, this is a decimal, so we need to round this up to the next larger whole number, which is 20. So we're looking for the 20th number that's in that data set. That would tell me the 80th, the number that's in the 80th percentile.
71.
That'd be 71. Okay. All right. Are there any questions about problem number 1?
Can you take a look at B again?
Okay. Okay. All right, anything else? Okay, number 2 is this. And number 2, the data below represents the number of bills enacted by Congress during the last several years. And here we want to complete the following. Part A is the file number summary, and then construct a box plot for this data set or set of data. Now, what I would do first is sort that data set in numerical order from smallest to largest. So for the sake of time, this is the data set that's going to be sorted from least to greatest. Okay. Okay. So for part A, we're going to do the file number summary. And in the 5-number summary, you need the minimum. You also need Q1, the median, which is also the same as Q2, then Q3, and then your maximum. All right, so what's the minimum number in this sorted data set?
88,
88. And the maximum?
14.
410. Those two are easy to find. Now for the median, we need the middle number of this sorted data set. And if you go in the middle, you're going to see that it will be 198. So the median, 198. Now we need to know what Q1 and Q3 are going to be. Okay. I think someone already said it. But if you didn't know, Q1 was the 25th percentile. And of course, L, we find that by doing K over 100 times N. So it'd be 25 over 100 times 9, because there are 9 data values here. So 25 divided by 100 times 9 gives us 2.25, but we need to round that up to 3. So the third number in that data set will have to be 153. That's your Q1. Now for Q3. Now Q3, if you recall, represents the 75th percentile. And of course we use L is equal to K over 100 times N. So it's be 75 over 100 times 9. So what's 75 over 100 times 9? 6.75, which rounds up to 7. So what would be the 7th number in that data set? 241. Okay, so Q3, the third quartile would be 241. Okay, now that right there represents the 5-number summary. Now in part B, they want you to use that 5-number summary to construct the box plot for this data. Okay, so here's what we're going to do here. I need a number line like this. And looking at this, starting at 0, this goes up to 410. So I'm going to do this in increments of 100. So I'm going to say 100 will be here. 200 would be here. 300. 400. Let's extend this out a bit to 500. Okay. The smallest is your 88. So I'm going to draw a small vertical line there, close to 100. 410 is a little bit past 400, so I'm going to draw another small line like this. Let's see. Q1, the median, and Q3 make up the box. These two make up my whisker. So here, Q1 is 153, so that's halfway between 100 and 200. So I'm going to draw a longer line here. And then 198 is close to 200. So I'm going to draw another equally long line here, close to 200. And then 241 would be about right here. So I'm going to draw another longer line like this. Those three make up the box. And to draw the whiskers, that minimum will be connected to Q1. The maximum will be connected to Q3, like this. So this will be the box and whisker plot, or the box plot for this data set. Okay. Are there any questions about problem number 2? All right, problem number 3.
For like the Q1 and Q3, on 2, if you already know that it's an odd number of data values, do you have to show the formula, right? Like if you already know it's an odd number and you can see that it's, if you already know that it's 153, do you have to show that part, the K
Yeah,
100?
yeah, you have to. Because I'm going to tell you, because sometimes it's hard to see what's in the 25th percentile. Because you have to know where it's located. Because these numbers tell you the position where the number is located in as the 25th percentile or the 75th percentile. So you need to try to do that. Okay, any other questions? Okay, now number 3. If the probability of event A is 0.912, what is the probability of the complement of A, which is what A bar means? So you have the probability of event A, that's going to be 0.912. So to find the probability of A complement, that's going to be 1 minus the probability of event A. So we subtract 0.912 from 1, and we'll get what?
0.088.
Yeah, 0.088. Okay. Any questions on number 3? All right, number 4. 17 of the 100 digital video recorders in an inventory are known to be defective. What is the probability you randomly select an item that is not defective? Well, we know that the probability of selecting an item that is defective well, 17 are known to be defective, so it'll be 17 out of 100. And what's 17 over 100 as a decimal? 0.17. So now we want the probability. We randomly select an item that is not defective. So in that case, it's just a complement. Those two are complements, so it'll be 1 minus the probability of selecting a defective item. So what's 1 minus 0.17?
0.83.
0.83. Okay. Okay. Are there any questions about problem number 4? All right, number 5. Refer to the sample data below and complete parts A through D. All right, so in part A, the question is, how many responses are summarized in the table? So here we just have to add those four numbers that you see in that table, and that will tell you the number of responses that are summarized. Okay, so what's 11 plus 34 plus 44 plus 8? 97. So that means that there are 97 responses summarized in that table. Okay. Now, part B, how many times did the polygraph provide a negative test result? 42. Here's negative test results, the 34 and 48. So we do this, just add those two numbers together. 34 plus 8, 42. So all of that was part B. Part C. If one of the responses is randomly selected, find the probability it is a negative test result. So we're looking for the probability that one of the responses randomly selected came out to be a negative test result. Well, how many negative tests were there? 42. Out of the grand total of 97. And we'll just leave it as a fraction, 42 over 97. Okay? Because in part B, they just asked for you to express the answer in part C as a decimal. And we're going to say to 3 decimal places.
1433.
Okay, so if you do 42 divided by 97, we have a 2 in the 3rd decimal place. The 9 makes it 2 or 3, so it'll be 0.433. Okay. So in decimal form, that would be the probability of randomly selecting a response with a negative test result. Okay, questions on problem number 5. Okay, now problem number 6. All right, in number 6, the following data summarizes results from 1,071 pedestrian deaths that were caused by accidents. All right, and it says here, if one of the pedestrian deaths is randomly selected, find the probability that the pedestrian was intoxicated or the driver was not intoxicated. Okay, so in this case here, we have to use the fact that we have the probability of A or B, which is this, the probability of A plus the probability of B. And if there is an intersection of the two, or if there's something in common for both A and B, we have to subtract off what's common in A and B. So if you look at this, we're dealing with the probability that the pedestrian was intoxicated, so that will be this column here, or the driver was not intoxicated. That will be this right here. Notice that there is a overlap in between for those two. All right, so what we're going to do here, find the probability that the pedestrian, and I'm going to abbreviate here, was intoxicated, or the driver not intoxicated. That's going to be equal to the probability that the pedestrian was intoxicated plus the probability of the second where the driver was not intoxicated. And then we subtract out the overlap. The probability that the pedestrian was intoxicated and the driver was not intoxicated. Okay. So now, let's find out the probability that the pedestrian was intoxicated. That's this column right here. How many pedestrians were intoxicated? 375. You add 75 and 300 together, you'll get 375. And this is over 1,071, which was given to you. And then plus the probability that the driver was not intoxicated. How many were not intoxicated?
96.
How much? 896? Yeah.
So you add the 300 and the 596.
Yes. 300 and 596 gives you 896. And that's going to be over 1,071. Minus. Now, we're going to find what's in common for both the pedestrian being intoxicated and the driver not intoxicated. In this case, here's that intersection right here, 300. Where the pedestrian was intoxicated and the driver not intoxicated. That's 300. Because that's the overlap. That's over 1,071. Well, the denominators are the same, so we can just go ahead and add 375, 896, and subtract 3,000 from that. And we will end up with what? 971 over 1,071. And let's say I want that as a decimal to 3 decimal places. Yeah, 0.907. That would be the 3 decimal place probability. So the probability that a randomly selected pedestrian deaths, well, the probability that the pedestrian was intoxicated or the driver was not intoxicated would be 0.907. Okay. Are there any questions about problem number 6? Okay, number 7. Here we're going to refer to the table, and we're given that 2 of the 215 subjects are randomly selected, and we're going to complete parts A and B. In this case here, if the selections were made with replacement, what is the probability that the 2 subjects are both group A and type RH? Okay. So here's group A, which is over here, type RH plus. That would be this row right here. And of course, and is the intersection of the 2. Now, in part A, it does say with replacement. So that means that the probability that the first person that's from group A and RH type group A and RH plus. What's that number?
62?
62. That's, yeah, I just highlighted RH plus and then group A, the intersection 62. So it'd be 62 out of, what, 215? All right, and now for the probability that the second person is from group A and has a type RH plus. Now this is with replacement, meaning I select one, that person goes back in, and then I select the other one. What would that probability be?
61 out of 215?
Not 61. 60, it's still 62 out of 215. Okay, with replacement, it goes back
I was
in.
thinking it's still without.
Okay. So now, to find the probability that two people are from group A and type RH plus, we just multiply these two together. So it'd be 62 over 215 times 62 over 215. And we're going to get a decimal value from this. That's how we enter that in, and then hit enter. And to 3 decimal places, what would that value be?
0.083.
Okay. So this represents the probability that two selected subjects are both group A and type RH plus, 0.083. And that's part A right there, with replacement. Now part B is without replacement. That means the first subject is selected, and that first subject will not be considered for the second selection. So we already know what the probability for the first person from group A and type RH plus, that's 62 over 215. Now without replacement, the second person, the probability of selecting the second person from group A and type RH plus is now going to be what? 61 over 214. Because when that first person is not put back in, that means the numerator and the denominator decreases by 1. So instead of 62, I have 61. And instead of 215, I now have 214 to choose from. And we're going to multiply these two together as well. So the probability that two people randomly selected are from group A and type RH plus. So 62 over 215 times 61 over 214. Okay, and then times 61 divided by 214. To 3 decimal place, that would be what? Wait a minute, that should be 62 over 215. I made a mistake. 62 over 215. The other one's 61 over 214. Now the two decimal places, what would that be?
0.082.
0.082. All right. Any questions about problem number 7? Okay, in problem number 8. Problem number 8 says that the data represents the membership of a group of Republicans. If we randomly select one politician, what is the probability of getting a Democrat given that the male was selected? All right, so that's one of those conditional probability problems here. Now, we're given that the male was selected. That would be this row right here. So we're only going to be focusing on the male right here. How many males are there?
47, or all of them? Sorry.
All of them total, 100. So that would be your denominator. Because what conditional probability does, it reduces the sample size. And the probability of selecting a Democrat given a male, how many Democrats, of all the males, how many are Democrats? 47. So that 47 goes in the numerator. So it'd be 47 over 100. And I'll just say 0.47. Because that's what it'll give you on the calculator. 47 divided by 100, which is 0.47. Any questions on number 8? All right, number 9. In this case, we're going to find the probability of winning the lottery in which one selects the 6 winning numbers from 1 to 22 in any order with no repetitions. Okay, that's one of those combination problems here. There are 22 numbers, and we're going to choose 6 of them. Okay. So the way we're going to do that is this. I'm going to type in the number that's on the left-hand side, which is your 22, and then select the math button. We're dealing with probability, so we're going to use our right arrow key to highlight this menu that says PRB. The C is in the middle, so we're going to select NCR, which is number 3. You can go down and press enter. And then we enter the number on the right side, which is just 6. And then press enter. And it should give you this number, 74,613. Okay. Now we want the probability of winning the lottery. If one selects the 6 winning numbers from 1 to 22 in any order with no repetitions, how many ways can we win?
74,000.
Well,
One.
it's just one.
Oh, yeah, one.
There's
out.
one out of all those numbers. There can only be one winner. So the probability of winning would just be 1 over 74,613. Okay, and that's all there is to it.
So how do you know the difference between NCR and NPR? Like, you know, which one?
It says in any order, so order doesn't matter, so it's a combination problem. If order does matter, then,
Okay, then it would be that PR one.
yeah. Mhm. Any other questions? Okay. Problem number 10. Okay. All right, in problem number 10, this is where table A-2 will be coming in for the rest of these problems here. Assume that the thermometer readings are normally distributed with a mean of 0 degrees Celsius and a standard deviation of 1.00 degrees Celsius. Draw a sketch and find the probability that a randomly selected thermometer will have a reading less than 0.24. Okay, so first of all, we need to draw the sketch. And I will tell you this, on the exams, you will be expected to draw a sketch of the normal curve, because that helps you see what's going on. And we're told that the mean was 0, standard deviation 1.00, and we're looking for the probability of randomly selecting a thermometer with a reading less than 0.24. So 0.24 will be somewhere over here. And anything less than means I need to shade either to the left or to the right. Do I need to shade to the left or to the right? Less than means to the left. All right, so it's going to be this part that I'm going to be looking for, this shaded area. And of course, if you do the z-score, it would be x minus mu divided by sigma, the standard deviation. The x was 0.24. The mu, which is your mean, that's 0, divided by the standard deviation of 1.00. And this is going to be quite easy, because that numerator is just going to be 0.24 divided by 1.00, which is 0.24. So to find the probability that our z is less than 0.24, this is where we use table A-2. And it's a positive z-score, so we have to use the side of the page that says positive z-scores. So we find 0.2 and 0.04. That would give us what? 0.5948. So that represents the probability of selecting a thermometer, randomly selecting a thermometer with a temperature reading less than 0.24 degrees Celsius. Okay. Are there any questions about number 10? All right, number 11. Says find the critical value for z sub 0.05. Now, when we're dealing with the critical value, that 0.05 represents the area from the right. So that 0.05 is this part, and it's that area to the right. And we want its critical value. But if we're going to use table A-2, it calls for the cumulative area from the left. So that means here, if this area to the right is 0.05, what must this area to the left be? 0.95. And you know what I'm going to do here? Add 2 zeros behind it, since I'm using table A-2. And 0.95 is positive. Is greater than 0.5. So I need to use the page that says positive z-scores here. Now, if you try to find 0.9500, it's not in the table. But if you notice that asterisk there, it leads you to something down here at the bottom of that page. So if you go down and read to the left and you find 0.9500, what would be that z value? 1.645. That would be your critical value. So z sub 0.05 is 1.645. What was that again?
How do we find that?
1 minus that 0.05, since the area underneath the curve is 1. Okay. Any other questions about problem number 11? Okay, problem number 12. Assume that adults have IQ scores that are normally distributed with a mean of 100 and a standard deviation of 20. Find the probability that a randomly selected adult has an IQ score between 84 and 116. Okay. So we just need to draw a normal curve. Now in this case, the mean is 100, and the standard deviation is 20. And we're finding the probability that a randomly selected adult has an IQ score between 84, and here 84 is less than 100, 116 is to the right of 100. So we're looking for the area in between those two. Okay, so that's the shaded area that we're looking for in this case. All right. So we need to convert 84 and 116 to z values here. So let's start with 84 for x equal 84. our z-score will be x minus the mu, which is your mean, divided by sigma, that's the standard deviation. So x is 84, so that would be 84 minus your mu, which is your mean, that's 100, divided by the standard deviation of 20. Now what's 84 minus 100?
Negative 16.
Negative 16. Negative 16 divided by 20 as a decimal would be what?
Negative 0.8.
Negative 0.8. And I'm going to add a 0 behind it, so it'll be negative 0.80. Now let's use table A-2 to find the area to the left. The z-score is negative, so we need to look at negative z-scores here. So negative 0.8 is way down here, 0.00 is here. What would that decimal value be?
0.2119.
0.2119. And that represents this area to the left, 0.2119. And now for x equals 116. We'll convert that to a z-score as well. So now x is 116 minus mu, that's 100, divided by sigma, the standard deviation of 20. So what's 116 minus 100? 16. And 16 divided by 20 would be 0.80. And now it's positive. So now we look at the page for positive z-scores. So we find 0.8 and then 0, 0. This time it's now 0.7881. That's the area to the left, by the way. So the area to the left is 0.7881. So that's over here. All right, so 0.7881, that's the area to the left. Now to find the area in between, we subtract those two. So that means the probability that a randomly selected IQ score is between 84 and 116, we subtract 0.7881 minus 0.2119. And that's going to give us what? 0.5762. Okay. All right. Are there any questions about number 12? All right, problem number 13. Assume that adults have IQ scores that are normally distributed with a mean of mu equaling to 100 and a standard deviation sigma equaling to 20. Find P4, and that represents the IQ score separating the bottom 4% from the top 96%. Okay. So here's another normal curve. Mu is 100, standard deviation of 20. P4 is going to be on the left-hand side because that represents the bottom 4%. And the bottom 4% would be this area to the far left. And what's 4% as a decimal?
0.04.
0.04, and I'm gonna add 2 zeros to that. Okay, now I need to know what its corresponding z value is gonna be. Well, 0.04 is less than 0.5, so I need to look at the page where it says negative z-scores. And look in the body of the table and find a value that's close to 0.04. Well, I see 0.0401. So to the left and above, negative 1.75. That would be your z value. Okay. And then to find out what the x value is, we're going to use this. X is equal to mu plus z multiplied by sigma. The mu is your mean, which is given to be 100, plus, we found out what z is, that's the negative 1.75, times sigma, that's given to be 20. So to find out what our x value is going to be, we have 100 plus negative 1.75 times 20. It'd be 65. So the IQ score that separates the bottom 4% from the top 96% would be 65. Okay. Any questions about problem number 13? All right, and problem number 14. Here we have to use the central limit theorem. Assume that women's heights are normally distributed with a mean given by mu equaling to 63.7 inches and a standard deviation given by sigma equaling to 1.9 inches. Part A says this: if one woman was randomly selected, find the probability that her height is greater than 64.3 inches. All right, so let's start with part A. Okay, so all I need here is just a normal curve. And then the mean was 63.7. Standard deviation was 1.9. And 64.3 will be somewhere to the right. And it says greater than 64.3 inches, so do I need to shade the area to the left or to the right?
Right.
To the right. So it's going to be this area that I'm going to be shading. All right. Now, this is where we convert to a z value. And it does say if one woman, so that means our sample size n is going to be 1. So we must use this z formula. Z is equal to x minus mu divided by sigma. So that means our x value is 64.3 minus mu, that's 63.7, divided by sigma, that's 1.9. And if you choose to do this in the calculator, you need to put this in parentheses. So that means left parentheses 64.3 minus 63.7, close parentheses, divided by 1.9. And to two decimal places, what would that z value be? 0.32. All right. Now we're going to use table A-2 to find 0.32. It's a positive z value, so we have to look on the side that says positive z-scores. So 0.3 and 0.02 gives us what? 0.6255. However, that 0.6255 represents this area to the left, which is not what we're looking for. We want this shaded area to the right. So that means if we want the probability that some x is going to be greater than 64.3, I need to do 1 minus 0.6255. And what's 1 minus 0.6255? 0.3745. Okay, so that right there is part A, where we're finding the probability that a woman's height is greater than 64.3 inches. That's just for a single woman. In part B, they ask this question. If 10 women are randomly selected, you want to find the probability that they have a mean height greater than 64.3 inches. Okay, so now we don't necessarily need to draw another normal curve, but we are given that n is equal to 10. So instead of using this z formula in part A, we have to use the other z formula. And that's going to be this one, z is equal to x, and it's going to be x bar, because they say it has a mean height. So x bar minus mu divided by sigma, standard deviation, divided by the square root of n. Okay? This time your x bar, which is your mean height, that's 64.3. Minus the mu is still 63.7, divided by sigma, that's still 1.9, but that's going to be divided by the square root of n, and n is 10, so it'll be the square root of 10. Now if we use the calculator, this needs to be in parentheses. This down here needs to be in parentheses as well. So let's do the calculation here. Left parentheses, 64.3 minus 63.7, close parentheses, divided by, the denominator will be in parentheses, so left parentheses, 1.9 divided by, for the square root of 10, second x squared for the square root, and then type in the number 10. Use your right arrow key to get out of the square root, close your parentheses, and hit enter. Now, to two decimal places, that's going to be what?
1.
A 1. And I will write this as 1.00. Okay. Now, positive z-scores, 1.0 and 00 gives us what? 0.8413. But keep in mind, it's the area to the left. We're looking for the shaded area on the right. Okay, because it does say greater than. So we need the area on the right. So that means here, that the probability that your mean is greater than 64.3, we have to do 1 minus 0.8413. And what's 1 minus 0.8413? 0.1587. So that means here that the probability that 10 randomly selected women have a mean height greater than 64.3 inches would be 0.1517. Questions on part B? All right, so now part C, they ask the question, why can the central limit theorem be used in part B even though the sample size does not exceed 30? Well, one of the requirements for using a central limit theorem is that your population has to be normally distributed. So you were told in this problem that the heights of women are normally distributed. So that's why we can use the central limit theorem. So we can say something like this. Women's heights are normally distributed. Okay. Any questions about part C? Or any questions about number 14? Or does anybody have any questions about what will be on exam number 2?